Let's look at the acids and bases, salts now. And yes, acids and bases are a huge chapter. Okay, and so yes, be patient. There's still a little bit more coming. But anyhow, let's look at this little portion where when acids and bases react, they give salt and water. So let's look at these salts, okay, of acids and bases. So depending on what kind of a reaction you're talking about, all the neutralization reactions, which means acid-base reactions, are going to give you salt and water. The salt and water can be acidic or basic, depending on the strength of the acid and base. Okay, and so now remember, we're talking here only about the Bronsted-Lowry and the Arrhenius acid bases. We're not really talking about Lewis acids and bases here. So keep that in mind. It's not for Lewis acids and bases. Neutralization is only for, again, just the Bronsted-Lowry acid base. So first scenario is when you can have a strong acid reacting with a strong base, like HCl reacting with sodium hydroxide. And what this will give you is a neutral salt. What does a neutral salt mean? A neutral salt means that if you take the conjugate acid and the conjugate base, the conjugate acid is sodium, the conjugate base is chlorine or chloride, and if you take those two and treat them with water, you will not get any reaction. The sodium ion will not do anything for water and the chloride ion does not do anything for water. So there is no reaction, okay, with these, which means that the solution that you ended up getting here from a strong acid and a strong base is a neutral solution. pH is equal to 7. All right. When you have a strong acid and a weak base, now you will get a weak conjugate acid as a solution. All right. What does that mean? So HCl is giving you the hydronium ion, which is then reacting with the base over here. The base is taking the proton from here. So if you have a weak base will give you a stronger conjugate acid. Okay, remember that from when we learned about conjugate acids and bases. And so a strong acid will give you a weak conjugate base, which was a theory behind here too in the strong acid, strong base thing. But here it is a little bit more obvious because now we're dealing with a weak base. So weak base give stronger conjugate acids. So if you have a stronger conjugate acid, then the conjugate acid is going to now start reacting with water and you will have a slight equilibrium where you have ammonia and then the hydronium ion, which means that the ammonium ion, the weak conjugate acid that was formed, is further reacting with water, okay, to give hydronium ion. So this is after neutralization, after you've done the reaction, after everything is done, and if you check the pH of the solution, you will find the pH of the solution to be acidic, okay, and that is normal, it's okay. So which means that complete neutralization did not take place, which means that the pH is not 7. The pH of this solution is going to be slightly lower than 7 because you have an acid in there, okay, and the acid is coming from the weak base. Remember that. If you have a weak acid and a strong base, then the weak acid is going to give a stronger conjugate base, and the stronger conjugate base can then react with the water to give hydroxide ion. So which means that in this case you will have a slightly basic solution. This essentially is it as far as knowing whether you will have an acidic solution or a basic solution. Is if you're clear in your mind about what weak bases are and what weak acids are, then you will know exactly what kind of solutions will be formed. Okay, so if you have a strong acid, strong base, neutral salts. If you have a strong acid and a weak base, the weak base will give you a stronger conjugate acid, which means that you will have acidic solution. If you have a weak acid will give you stronger conjugate base, which means your solution is going to be basic. All right, that is what the flow of thought can be. So in general, here I've given you some examples, okay, of what kind of acid base you can find and what kind of salts you will form. So a cation, and that gives you a solution that is acidic. If you have an acidic solution, remember you're talking about a weak base, okay, in here. So you're talking about the conjugate acid of a weak base, which would be these over here. So the NH4 plus is coming from NH3, the CH3 NH3 plus is coming from CH3 NH2, and a small highly charged metal, okay, so any of these. I highly doubt that you're going to see the cations over here. Mostly, I'm sure you will see something like ammonia, okay, and its derivatives. An anion that makes a solution basic is going to be the conjugate base of a weak acid. Okay, so for example, these ones. Anything that does not affect the pH of a solution is, of course, the group 1 salts, because group 1 bases are very strong bases. Okay, and so they will not give you any kind of acidic or basic salt. And any kind of an anion is going to be coming from the conjugate base of a strong acid. So strong acids, strong bases, no. Okay, you will not have any pH for that. Okay, or it'll be a neutral pH for that, I should say. So look for the strong acid, strong base. That's what will be the questions that are usually posed to you is, well, here is a salt. Is the solution going to be acidic or basic? So let's do that. So here is what we have to do if we are trying to figure out whether you have an acidic salt or a basic salt. There are 3 steps. To take a salt, then break it down into its anion and cation. See what the conjugate acid and base is, and then you determine the acidity and basicity. So we're going to start with sodium bromide. Sodium bromide, sodium ion is the conjugate acid of sodium hydroxide, which is a strong base. So a strong base meaning that you don't get a good conjugate acid from it. Okay, strong bases give you weak conjugate acids. Bromide is the conjugate base of HBr, which is a strong acid. So if you have a strong acid, it gives you a weak base. So strong acid, strong base, neutral salt, because you have weaker conjugate acid and weaker conjugate bases. Okay, so it's a neutral salt. Sodium acetate. As soon as you see sodium, it should come into your mind that you're getting the sodium from sodium hydroxide, which is a strong base. If it's a strong base, cross it out. That's it. Strong bases give you weak conjugate acid. So that's not happening. Okay, so sodium is not happening, which means you need to look at the acetate. The acetate is coming from acetic acid, and acetic acid is a weak acid. So if it's a weak acid, it will give you a stronger conjugate base. So if you have a stronger conjugate base, it means your solution is going to be basic. Okay, all right. And then ammonium chloride. You're looking at ammonium chloride. Chloride over here is coming from HCl, which is hydrochloric acid, which is a fairly strong acid. So if it's a strong acid, it gives you a weak conjugate base. So if it's a weak conjugate base, you can cross that one out, which means that we are focusing on the ammonium ion. Ammonium ion is the conjugate acid of ammonia. Ammonia is a weak base. If this is a weak base, you have a stronger conjugate acid. If you have a stronger conjugate acid, you have an acidic salt. Okay, it's as simple as that. You should keep it as simple as that. Don't try to make it complicated for yourself. If you want, you can write these things out where you have a strong acid plus strong base is equal to neutral salt, and these equations that I've written out here for you, because this is kind of what will help you in some ways if you forget the other part, which you shouldn't forget the other part, because that's how you would work it out. So again, here's some more examples, okay, of trying to figure out if something is acidic or a basic salt. So ammonium nitrate is administered as an intravenous solution, blah, blah, blah. And so would this substance be used for acidosis or alkalosis? Okay, so which means that they're trying to figure out if ammonium nitrate is actually going to be an acidic or a basic solution. So if ammonium nitrate is what you have, then you break it down into ammonium ion and nitrate ion. Ammonium is coming from ammonia, again, that is a weak base, which means that you have a stronger conjugate acid, so this is slightly acidic. Nitrate is coming from nitric acid, and if it's coming from nitric acid, it is a strong acid, which means that the conjugate base is neutral. So if this part is neutral, but the ammonium is acidic, which means your salt is going to be slightly acidic, which means that if it is an acidic salt, you cannot use it for treating something that is already acidic, which means that you can use it for alkalosis, okay, which means that if you need to neutralize something, then you will neutralize a base with an acidic salt. All right, so alkali stands for basis, and so it will be used for alkalosis treatment because ammonium nitrate is an acidic salt. Then you can also figure out if you have an acidic salt or a basic salt by looking at Ka and Kb. Okay, Ka and Kb is of course for acids. All right, so for example, if you have Ka, which is more than the Kb, then solution is acidic. Very simple. If Kb is larger than Ka, then your solution is basic. If they're both equal, it's a neutral. Okay, solution. So for example, the Kb for ammonia. Okay, using the Kb for ammonia. For ammonium ion, Ka is Kw over Kb. Okay, remember Kw is equal to Ka times Kb. Alright, so Ka for ammonium ion is 5.6 times 10 to the negative 10 after doing the calculation. Where do you get the Kb from? That is from the data tables. And then Ka for HF. Alright, so for fluoride ion, the Kb for this, because fluoride is the conjugate base, so you're looking at the Kb for this, and the Kb for this then is equal to 1.5 times 10 to the negative 11. Just simple calculation, Kw divided by the Ka or Kb. So when you're looking at the Ka and Kb for these two ions, you can see that the Ka with a lower negative number is larger. Okay, so if it is larger, that means that NH4 and NH4F, which is ammonium fluoride, is an acidic salt. Okay, so this requires a little calculation, but this is not very hard calculation to do. All you need is the Ka and the Kb values for the acids, okay, and the bases for it. And once you have this, then you can figure it out. And sometimes these things are a little bit harder to do just by knowing your strong acid and strong base, because if you think about it, ammonia is a weak base and hydrofluoric acid is a weak acid. So if both of them are weak acids, then how do you figure out if your salt is going to be acidic or basic? Because if one of the components is strong and the other one is weak, then you know that the weak will give you a strong conjugate acid or base. But if both of them are weak, then how do you determine this? So this little exercise here is really good if you have a salt of a weak base and a weak acid. Okay, so then you compare the Ka and the Kb for the ions, and then you figure out whether your salt is acidic or basic. So in this case, it turned out to be acidic. So let's look at a calculation of pH of a salt solution. Obviously, if you have a salt solution that is acidic or basic, you can calculate the pH or POH of it. So depending on what the question is asking you, let's try and do this one. Determine the pH of a 0.525 molar solution of pyridinium nitrate at 25 degrees Celsius. So useless information, 25 degrees Celsius, who cares? All right, pyridinium nitrate dissociates in water to give pyridinium ions, and which is this, and then Kb is given to us, and then of course we have nitrate ions also in the solution. So we're supposed to figure out the pH of a 0.25 molar solution of pyridinium nitrate. Now, just by looking at this equation, you know that the nitrate is coming from nitric acid. So which means that it's coming from nitric acid, that's going to be a strong acid, weak base, which means that this must be then the stronger conjugate acid. So if this is a stronger conjugate acid, it means that you're going to have a hydronium ion in there, okay, and not base. So because the base is coming from a strong acid, okay. All right, so we are given the Kb of this because Kb is for pyridine, all right. And so for pyridine, if Kb is given, we have to calculate Ka because we are being asked to calculate the pH of the solution. This is one of those little things that you really have to pay attention, okay, because you might just miss it, and it will just change all your calculations, okay, for it. So please make sure that you pay attention if you're dealing with pH and if you're given Kbs and whatnot, all right. So if you have to calculate the pH and you're given Kb, you gotta get the Ka, all right. So calculate the Ka from the given Kb, and this is what you end up getting, 5.9 times 10 to the negative 6, all right. And so then Ka setup is going to be like this. These concentrations here for the pyridine and the pyridinium salt are coming from this equation over here. Now, it's sometimes initially it may be hard for you to figure out how to write this equation, but don't freak out because really all you have is an acidic salt which is reacting with water to give you back the conjugate base. So remove the proton and then you have the hydronium ion there, okay, from the base. So if this is the acidic salt, this is the proton donor, and your proton acceptor, the base is always going to be water, okay, because this is going to be dissolved in water. So it's really not that hard to write this equation. Maybe it's given to you, but if it is not, don't worry about it. Okay, and the most important thing you need to remember is you're dealing with an acidic salt. So if you're dealing with an acidic salt, you will have hydronium ion concentrations in the product. Okay, so we're starting with 0.25 molar solution. So initially you have nothing of the hydronium ion. There is a change going on, and then of course we have the equilibrium. We've done this before, and so 0.25 minus X at equilibrium, and then X and X at equilibrium for hydronium ion and the pyridine, which is the conjugate base then. Then you set up your values over here, okay, which is taking this Ka and then putting in all the numbers here, which is the x's and all that. This is blocked out. Don't worry about that because there was a little typo there. It said KB, but it's supposed to be KA. So don't worry about that little black spot. You're going to ignore minus X because if you're dealing with a weak salt solution, acidic salt solution, then X is going to be insignificant as far as subtracting it is concerned. All right, and so this is going to be your equation then. X squared over 0.25 is equal to 5.9 times 10 to the negative 6, which was the Ka of the salt. So then you calculate for X. Once you have the X, then you will figure out, of course, the pH, because X is then the hydronium ion concentration. And you can see that even such a dilute solution of pyridinium nitrate, which is supposed to be weak acidic salt, the pH is about 2.92, which is fairly good, okay, for this. So that's the pH, and that's how you would do the calculation for this. If you wanted to know, again, whether you needed to use X or not over here, you can go ahead and do a slight check, okay, and then see that the ionization is less than 5%. Although I can tell you that you probably will not have to do this cross check all the time, so don't waste time in an exam. The only time you should not ignore X is when you're calculating the pH for diprotic acids, but other than that, you can ignore X pretty easily. So here is another calculation for the pH. Household bleach is 5% solution of sodium hypochlorite. This corresponds to a molar concentration of about 0.7 molar sodium chlorate. What is the hydroxide ion concentration and the pH of the solution? And the Ka is given to us. So if Ka is given to us, then we are dealing with a weak acid over here. However, if you're dealing with a weak acid, you're actually dealing with a stronger conjugate base when the reaction happened. Okay, so look at the salt again. It is sodium chlorate. The sodium is coming from strong base, which means this is meaningless. This is coming from a weak acid, hence the Ka. So coming from a weak acid, it means you're getting a stronger conjugate base. If you're getting a stronger conjugate base, it means your salt is basic. All right, so which means that the pH of your salt solution over here should be more than 7. That is your clue whether you're also on the right track or not. Okay, so first try to figure out what the approximate pH would be for this, whether it is above 7 or below 7. Okay, just by looking at the salt. So anyhow, so ClO minus, the hypochlorite ion is coming from hypochloric acid, which is a weak acid, strong conjugate base, so which means that we have a basic solution at our hands. So the first thing we will do then is calculate Kb, okay, because now we're dealing with a basic solution. So Ka is given to us. We're going to convert that into Kb using the Kw as we did in the previous slide. Okay, so I'm not showing the calculation here, but I'm sure you can do that. So once you have the Kb value, and here is your equation set up then, okay? And so now you can see that you have the hydroxide ion in solution, and again the hypochlorite ion, you're just reacting that with water, okay? There's nothing very specific about the reaction. And you have hydroxide ions in there, so you're starting with 0.70 molar of the sodium hypochlorite. Your ice method again, same thing. Okay, here is your Kb setup. And again for here, the minus x, you can go ahead and ignore that. I didn't even put that in here. So 2.9 times 10 to the negative 7, which is Kb, is equal to x squared divided by 0.7, because we're ignoring the x over here. So then x squared, and then x value is 4.5 times 10 to the negative 4. So which means that your hydroxide ion concentration is 4.5 times 10 to the negative 4. But that is hydroxide ion concentration. Okay, you're supposed to figure out the pH of the solution. Okay, so one part of our problem is done because we were supposed to figure out the hydroxide ion concentration. Now we have to figure out the pH of the solution. Okay, so pH of the solution is going to be, of course, 14 minus the pOH. So which means you can calculate the pOH using the hydroxide ion concentration, which is this over here, and then subtract it from 14. So then the pH comes out to be 10.65. I mentioned that to you over here in the beginning as we were starting this, that because your salt over here is slightly basic, your pH should come out to be higher than 7. Okay, so it kind of helps a little bit if you kind of know where you're going. So when you get your final answer, that you're on the right track. So the concepts from this little acid-base salt presentation is that you should be able to identify the acidic and basic salts, and then you should be able to calculate the pH of acidic and basic salt. And remember, the key thing here was converting the Ka to Kb and Kb to Ka, depending on what kind of a salt there is, okay, acidic salt or basic salt. So keep that in mind, and just don't be too fast, okay? Look at the data that's given to you before you start solving problems.